Hello and welcome to my presentation. My name is Pühringer and I'm a master's student at Johannes Kepler University Linz in Austria. I'm going to present our work on InstanceFlow, a tool for visualizing the evolution of classifier confusion on the instance level. This is joint work with Andreas Hinterreiter and Marc Streit. When training modern machine learning classifiers, such as neural networks, we often rely on the progressive improvement of specific metrics, for example, classification accuracy, recall, or precision. The most common way of visualizing this progression on a global level are simple line charts. But for specific tasks, such as multi-class classification, these are prone to hide important factors such as inner-class confusion and instance-level details. Related work on visualizing instance-level information has mostly focused on model-dependent parameters, such as the activation of neurons in response to a given input or the behavior of individual layers of a neural network. Similar visualizations exist for GANs and deep Q networks. Likewise, visualizations focused on the performance analysis of classifier typically do not enable a true temporal analysis. And additionally, most visualizations rely on the aggregation of instance information, such that instances are not directly accessible for further inspection. Previous work from our group is ConfusionFlow, a visualization tool allowing to access temporal metrics on the class level. The paper was recently published and is also presented at this conference, so make sure to join the talk given by Andreas. The temporal analysis is done by extending the widely used confusion matrix with a temporal aspect, showing aggregate scores such as accuracy in a heat map or line chart encoding throughout the epochs. By stacking different datasets vertically on top of each other, different classifiers or runs and their evolution per class can be compared easily. As a next step, and with the need of accessing specific instances directly, we built and now present InstanceFlow. The interactive visualization tool allows machine learning experts to inspect individual instances and their predicted class labels throughout training epochs. InstanceFlow consists of two main views, the flows view on the top and the instance ranking view on the bottom. The flows view visualizes the classification of the individual instances throughout the epochs using different aggregation levels. The ranking view on the bottom shows each individual instance and allows for a detailed inspection, including three metrics we defined for this paper. InstanceFlow was built to answer specific questions regarding the identification of difficult or oscillating instances, tracing an instance's classification history, or assessing class distribution and its changes throughout a given epoch range. In the following example, we're looking at a classification of the CFAR10 dataset. First, we start within a specific epoch. Here we see a box enclosed by purple dotted lines, which represents a prediction as cat. Within this container, the distribution of the real labels of the instances is shown. We then extend this for all selected classes, in our case dog as blue and deer as orange. Predictions as the other 7 classes are shown in the gray box in the center. Horizontally, we then show the same visualization for a selected epoch range. Within each of the prediction classes, we can see the distribution of the real labels of the instances predicted as such. To better understand the movement of instances throughout the epochs, Sankey diagrams are used to visualize the movement of instances from one class to another. In this case, many deer instances colored in blue were incorrectly classified as any of the non-shown classes in epoch 20. The Sankey diagram and the distribution of deer instances in the next epoch show that nearly half of the previously incorrectly classified instances are moving to the correct class. To avoid visual clutter, the distribution boxes can be hidden in favor of the flows, as the flows implicitly encode the distribution per prediction class. In the previous views, the instances were aggregated and shown as distribution bar chart of flows. The level of detail can be modified such that within each class prediction box, the actual underlying instances are shown. Each of these instances is encoded using glyphs, which indicate the stability in the current epoch of the instance. If specific instances are of interest, their corresponding classification paths can be traced, with correct and incorrect movements colored as green and red respectively. Again, the Sankey diagrams can be shown and they automatically highlight the included instances on hover. Clicking on this selected flow highlights the classification traces of all included instances. Below the previously described flow visualization, all instances are organized in a sortable, filterable, and flexibly customizable ranking using the lineup ranking technique. Each row contains a single sample showing the image for image classification tasks, as well as the ground truth label including color coding. Next, the prediction labels throughout the epochs for this specific instance are displayed as a colored heat map. To answer certain questions, such as which instances are visiting many different classes, which are oscillating between classes, or which instances are specifically hard to classify, we introduced three metrics. The frequency is the ratio of epochs in which the previous prediction is different to the current prediction. The variability is the ratio of how many classes in total were predicted for an instance across all epochs. And finally, the misclassification score of an instance is the fraction of epochs in which it was assigned to the wrong class. In the ranking, each row can be condensed to a few pixels to summarize and easily identify patterns. In our case, the condensed view of the prediction distribution reveals a pattern of successful learning, as the number of correct predictions, in this case purple on the top and orange on the bottom, become more dominant over time. To summarize each class with its instances, the aggregated view shows a histogram of all predictions. It immediately shows that the own class is predicted the most, but also reveals class confusion between cat and dog, for example. So with that, I would like to conclude this presentation. There is a link to the GitHub repository, which you can follow to find the full paper, these slides, an online demo with preloaded datasets, and the code implementation. Thanks for listening, and I'm happy to answer any questions.